Let's start exploring modern cryptography by taking a look at the primitive that is most familiar probably to everyone. When they think of cryptography, the first thing they think of is usually encryption. You hear this, it's in like I don't know, every sort of spy movie or episode of 24 or Homeland or whatever. It's always like, oh, let's crack the encryption, let's get the encryption going, let's get the guys from crypto to look at the encryption. Let's take a look at that. Here's a web page. This is the Kingston web page. So Kingston, you probably know, makes drives. In particular, they make high capacity USB thumb drives, and Kingston drives, like most other thumb drives, and in fact hard disks and solid state disks these days, they use what's called full disk encryption, which means that everything that's on the disk is encrypted when it's on the disk. And the reason for this is so that, if the disk is stolen, for example, the material that's on the disk is encrypted and can't be read, right? So this is intuitively what we think of as the security property of encryption, is that if you encrypt something and you were then to look at the resulting ciphertext, it's just completely scrambled mess, right? It looks like random bits. And we'll spend lots of time making these ideas about what encryption, what security properties it should have. We'll spend a lot of time actually making this formal later on. But roughly speaking, this is the kind of thing that you want, right? You encrypt a drive so that, and it's typically encrypted like under your password. So the password is used to derive some secret key for the encryption, and then the stuff that's on the drive is then encrypted, and the person who doesn't know your password can't then decrypt. So I picked this because I wanted to show you some examples of the kind of thing that you see in the glossy literature that comes with devices that actually use encryption. So here's Kingston, and they're doing you a service. They're showing you, they're explaining why it is their XTS encryption mode is the best way to do full disk encryption. And along the way, they're showing you some other modes of encryption. So here's one. Let's just start. This is like the easiest possible kind of encryption that we'll run into, and this is called the electronic codebook mode. And again, we'll get much more into this stuff there. But if you just look at the picture that's here, you'll see that what's happening. You've got some block of plain text. So maybe you can think about all of these blocks as being like blocks of a file that you're trying to encrypt before they go to disk. So if we've apparently taken this file to be encrypted and we've broken it into chunks. It doesn't actually say so, but each of these chunks or blocks is the same size. And in particular, they're the same size or the same number of bits as the number of bits that this object here takes in. This object, they've listed it as AES Inc., by which they mean the AES block cipher. So they're actually, AES stands for Advanced Encryption Standard, and ENC here is short for encryption, although that's really, as we'll come to understand, not really what's happening. It's actually enciphering that's happening, but that's a separate discussion. In any case, this file that we're trying to then encrypt and write to disk is broken into blocks that are, in the case of AES, each of these blocks is 128 bits wide. There's a key that gets shoved into the side here of AES. For the AES block cipher, this key is 128 bits wide. And then this block here magically takes this 128 bits of secret key material and this 128 bits of plain text and produces some block here of ciphertext. It doesn't say that this block is the same size as this block. Could be bigger, could be smaller. In fact, for AES, this block is the same size as this block. That's 128 bits. So we do this with each of the blocks of the file, and we get then a ciphertext that, because the size of the input blocks is preserved, the length of the ciphertext that's written to disk is exactly the same length as the plain text that was encrypted to start with. And as you can see here, they're showing you this is the standard thing to show that this is in fact a very, very bad way to encrypt data. If this was the thing, this was the file that you were trying to encrypt, this is what it would look like when you encrypted it with this ECB mode, electronic codebook mode of operation. So that's bad. But it already points out that the thing that's actually doing all the work in this encryption mode is this AES block cipher that's under the hood. Let's take a look at a different way. So this is something called cipher block chaining mode. So this is just another way of putting together the AES block cipher in such a way that you can encrypt large amounts of data. So here we've done the same thing. We've taken the plain text and we've broken it into blocks. And it's not immediately clear how big these blocks are, but we can see that the input here, well, this has to be exactly the width of AES, which we said was 128 bits. This symbol here, this circle with a cross in the middle of it, is pretty typical for bitwise exclusive OR. So I'll assume that you know what that means. And there's some value here called the initialization vector. Well, so if this is bitwise exclusive OR and this wire needs to be 128 bits wide, that tells us then that both this wire and this wire must also be 128 bits wide. So these plain text blocks, as before, are 128 bits wide. Okay, so far that's somewhat the same as above. We haven't said anything about what this funky initialization vector thing is, and we won't for a while, but it's some sort of startup string that the scheme gets. So you XOR this IV with the plain text to get a 128-bit string to feed into AES. The AES takes its secret key, and it produces, as we said above, 128 bits of ciphertext. This ciphertext block is then chained. So that's the name cipher block chaining. It's chained in to the next round, if you will, of this encryption, in which the second block of plain text is bitwise exclusive ORed with the ciphertext block that came in. That produces the next input for AES, which makes the next ciphertext block, and so on. This is, actually I just realized this is incorrectly labeled. It says this is ECB. In fact, this isn't ECB. This is CBC mode. CBC mode is actually a very good way to do encryption, and we'll say much more about how and why that's the case. But again, what we see is that here in CBC mode, what's actually doing all the heavy lifting is this AES block cipher that's under the hood. In fact, essentially all but maybe like one of the most commonly used encryption schemes, things that are used in SSL and TLS and IPsec and SSH, they all, if you were to draw them out diagrammatically, would have structures that look kind of like this or kind of like this. In fact, CBC mode, the one that's in this picture here, is probably the most commonly used encryption scheme in the internet. In the internet? All in the internet, I guess. In any case, all of them make use of a block cipher under the hood. And so we're going to start our slow build-up towards designing and analyzing encryption schemes by starting from the bottom with talking about block ciphers, what they are and what they're supposed to do. So let's, with that motivation at hand, let's do that. So let's start talking about block ciphers. Okay, so a block cipher is a special kind of an object called a function family. So let me introduce this idea first. This is our first bit of syntax. So I'll say before I start writing that whenever we introduce a new primitive in this class, so a primitive here is some kind of an abstract object that we're going to use to build other stuff. Whenever we introduce a new primitive, the very first thing we're going to do is establish the syntax for the primitive. You can think about this as being basically like, what's the API? What are the inputs and outputs that this kind of an object takes? And when we give this syntax, we'll always try to do it, try to give it formally and abstractly. So let me introduce first this idea of a function family. So maybe I just say here that a block cipher is a special type of function family. Okay, so I should tell you what a function family is then. So let's fix non-empty sets, calligraphic K, calligraphic D, and calligraphic R. Let's let F be a mapping from K cross D to R, be map. Okay, so we've got some arbitrary mapping here called F, and F takes elements from K cross D to R, where K, D, and R are these sets. Let me straight away introduce some notation here because this helps us get at the idea of what a function family is. So what would you write if you if you were talking about this object here mathematically? Then the kind of thing you would write is something like, well, if you have an input from K cross D, you would write something like F of K comma X. Yeah, this is saying that you run F on inputs. Something from K and something from D. So K is an element of K, and X is an element of D. And the output of this thing would be, let's call it Y. So I might as well just go ahead and introduce a bit more notation here. Let's say Y gets. Yeah, so this notation here, I just said the word. You read this thing here as, oops, I want to do that. I want to do it in a different color. Read this thing here as gets. Okay, so what do I mean by this? This notation here says that you run F on inputs K and X, and you assign, so this is assignment, you assign the output of this to the value Y. Okay, so that's simple enough. And you can think of F as being like a two-input function. But the equivalent way to think about this, and the way that we'll often do in this class, so equivalently, is to think of this, let me switch back to blue, as Y gets F, and we write the first argument K down as the subscript K of X. Y gets F sub K of X. Now, why am I saying these two are equivalent? Well, it's because what we actually do is we can think about F as being a two-input function, as we've done here, or we can think about the following. This equivalence here is using the fact that we can think of this two-input function F as actually a set of functions. So if I were to enumerate all of the K's that are in this set, we can think of the set of F sub K I. That's clear enough to read. F sub K I, where each of these maps from D to R, and where I is an element of the set 1, 2, up through the size of the key set K, or this, I'm calling it a key set because that's what it will be, but just some set K, right? We can simply define, we can think of this two-element function, so it's one function that takes two inputs, or we can think equivalently of, if I were to just fix a particular K and think about all the X's and where they go, all the Y's that they produce, that's what these are, right? So I can think about a set of functions that is equivalent to this. So where F sub Ki of X is defined to be F Ki of X, yeah? So we can have either the functional representation or the set representation, and this representation here is what we call a function family. Why? Because it's a family of functions. Each function is a mapping from the set D to the set R. And now we can think about this as a set. If we wanted to, we could index into this set by picking a particular value of k sub I. So that means if, let's say that, that the set k is the set of strings, maybe of length 128, then we can think about picking one element of this set by fixing one of the 128-bit strings, maybe the all zeros string. That's now an element of this set, yeah? And that's different from the function that would be named or indexed by choosing a different value of this k sub I. I hope that's reasonably clear, that these two alternative ways of thinking about this functional object here is either a two-input function or as a set of functions, that set being indexed by this value k. We'll usually use this latter representation when we talk about function families. We'll write things like this, but then we'll just say it's a function family. And when we say it's a function family, we mean that we think of this object as a set indexed by this first element. So maybe I'll just write that quickly so it'll be on the screen. Okay, so there we go. We have this idea now of a function family. And block ciphers, we say, are special types of function families. Why are function families going to be interesting for us? Well, if you think back for a moment to this picture that I just had up. Yeah, we had this picture and there was AES, the AES block cipher, and it was taking this key. So if we think about AES, we can sort of start to see that maybe this is kind of a function family because, well, it's taking in some key. So if we think about this key is coming from this set, calligraphic K, and we think about this input wire here as being a string that's coming from this set D, and the value that's on this wire here as being something from this set R, we can see that the AS, we can think of it actually as maybe being a function family. And what's naming elements of this function family are the particular values of the key. So this is one of the reasons that thinking about two-input functions, which AES is, as a function family is useful because it'll often be the case that when we're using, for example, function families like a block cipher, one of the two inputs will be very different semantically from the other. And in particular, if you think about AES, we've already talked about the fact that it's the key when you're doing encryption. It's the key that's the secret thing, right? The input may or may not be secret, I mean, depending on the security definition, but you can think of, you don't have to protect this thing typically in the way that you have to protect this thing. And so the semantics, the role that the key plays is very different from the role that this plain text input plays. And so it's convenient to think about indexing AES via the key, because that's the thing that's not known. This will get clearer as we go on. Right, so that's the idea of a function family, and we introduced a bit of notation. And let me explain to you why it is I said block ciphers are a special type of function family. Let me explain why that is. So let's, I guess we just go ahead and get rid of all this stuff for the moment. Okay, so let's again, let's fix, let's let E, so the usual notation we use for block ciphers is E, so let's let E be a mapping from, some more notation here, 0, 1 to the K. This is the set of bit strings of some length K, so I guess I should say first, let's fix integers K and N greater than 0. So let's let E, so E is going to take inputs that are K-bit strings, and it's also going to take inputs that are n-bit strings, and it's going to output n-bit strings, be a function family. Okay, so again, to be clear, it's taking in a k-bit string and an n-bit string and outputting an n-bit string. So what you can see, one thing is that the size of the input and the size of the output are the same, whatever they are. Okay, this is one property of a block cipher. So let me maybe write this in yellow. So this value here, n, this value is known as the block size. The block size of the block cipher. And it takes in blocks of n bits and outputs blocks of n bits. This value here, k, is usually called the key length or the key size. Key length. Why? Well, because this first input here, will usually write as k, and this is the key. This will end up being the key, the secret key typically of the block cipher. The next input here, we use different notations for it, x, d, but for the moment we'll just call it x. I'll try to stick with that for the lecture. This is the input block. We call this the plain text block. And this here is referred to as the ciphertext. Ciphertext block. Yeah. So we've already got these things. We've got a function family E that takes in a k-bit key and an n-bit plaintext block or just block, and it outputs an n-bit ciphertext block or again just block. We're saying let this be a function family. So of course when we say let it be a function family, what we mean is that we're going to be thinking of E not as E taking k and x as input, but as E sub k of x. So maybe just remind you. E.g. E sub k of x. That's the way we're going to think about this. Okay, so we haven't said anything yet about why this is a block cipher. All we've said is we've got some function family, and so syntactically that just means that it takes a k-bit input and an n-bit input, and it produces another n-bit input. So what's special about block ciphers is the following property. Then E is a block cipher if E is a block cipher when there exists an inverse mapping. And there exists an E inverse which again maps from k-bit strings across n-bit strings to n-bit strings. Such that E inverse sub k of E sub k, and this stylus is not picking up well right now. Let's try that again. Then E is a block cipher when there exists this mapping, E with the superscript -1 to give you the idea that this is an inverse, E inverse, which takes in a k-bit key and an n-bit string, another n-bit string, with the property that if you run the block cipher E with key k over input x, for any x that's in the domain, any x that's in here, if you run the block cipher over x, and then you immediately run this inverse mapping E inverse under the same key on the output of that, you get back x. Yeah? And vice versa, if you were to run this first and then this, you would again get back x. And so in other words, the way we usually shorten this is to say, in other words, something I didn't say a moment ago is that this is true not only for all x, but it's also true for every key k. Right? This inverse has to be computable for every x and for every k, which means, in other words, for all k, the mapping E sub k is a bijection or a permutation over n-bit strings. Okay, so that's a lot of math speak, particularly for people who aren't, using math speak all the time. So let's think about what exactly this is saying. We've said that we have function families, which are these two input functions, and we think of the first input as being somehow semantically different from the second input. The first input we usually think of as being like the key, and to sort of highlight the semantic difference between the key and the plain text block, we end up writing the key as a subscript, like outside, so that we have like, this is the mapping, E sub k is the mapping, and that mapping is typically going to be secret to anybody who doesn't hold the key k, right? So we've got this function family, and we're saying that function families are block ciphers. Maybe I should underline that. Function families are block ciphers when there exists an inverse mapping. In other words, no matter what key you fix, the mapping E sub k, the block cipher under the key k, is a bijection over this set 0, 1, n, so it's a bijection over its domain. And the usual way that we shorten that is just to say that a block cipher is a permutation over its inputs for every key k. That's the short way to say a block cipher with the key fixed is a permutation. Now, I went through this long road of writing that it's a bijection, i.e. permutation, because when I say permutation to computer scientists, they immediately think, oh, you mean like I have a list of numbers and I just reorder them. Yes, that's a special kind of a permutation. A permutation just means that, in the mathematical sense, you have a one-to-one and onto mapping, right, over some set. So, a bijection over n-bit strings is just a mapping that maps every x to a unique y and vice versa. So if we were to draw this sort of kind of set pictures, if this is the set 0, 1, n, And here's that same set again. What we're saying is if you take a point over here, so here's a point X. Every point X that you pick over here, if you fix a key K, then you get a mapping from X over here to some point Y. And this mapping is defined by E sub K. Yeah? If I had a different K, I'd have a different Y, potentially. I don't have to have, and I want to give you the idea that if I take the same X, this X here might map to this value, maybe Z, under some other key, E sub K prime, right? So what we have is that for every key K, so you can think of a key K and a key K prime, there is a mapping between every point X that's in this domain to a particular unique point over here, and that for keys, these mappings don't need to be the same, right? This is why we're thinking of this as being a family of functions, because for each one of these keys, we get some mapping from here over to here. And what we're saying it's a bijection, that means that you can uniquely go back. So if I were to start with the point Y and compute E sub K inverse, I'd get back X, right? So going this way is under E sub K. Going this way is under E sub K inverse, right? Likewise, if I started with Z and I went under E sub K prime inverse, I'd end up back at X again. So that's all it really means to be a bijection. And when we understand that that's what we mean, then we can just call it a permutation. And for those of you who do know a little bit, of these terminologies, the one-to-one part just means that for every X over here, there's a unique Y that's over here, and the onto part, which is the other part of making something a bijection, means that everything over here has something that maps to it. But in this case, the set is the same on both sides, so as soon as you have one-to-one, you get onto for free. Okay, so that's what a block cipher is. A block cipher is a family of permutations over some given set. Let me give you a particular example. So let's scroll this up a bit. So in those previous pictures, remember they kept talking about this thing called AES. So let me give you an example. So here's an example. This is AES, the Advanced Encryption Standard. AES is a kind of block cipher, and the syntax for AES could be written like this. AES is a mapping from keys that are 128 bits and plain text blocks that are also 128 bits to ciphertext blocks that are 128 bits. I did want to point out that all I've done so far is tell you that AES is a block cipher, and in particular that means it's an invertible mapping, and this particular invertible mapping for each key has a 128-bit key length and a 128-bit block size, right? So I haven't said anything at all about how this mapping behaves, right? I haven't told you if I give you any particular X, what particular Y it goes to, right? I haven't said how we build this thing. I just told you that if you looked at it from the outside, it's a black box. This is a box that has 2 input ports, and they each take 128-bit strings, and you can expect to get 128 string as an output. So we can generalize this thing. So if we think about all bijective function families that map from a 128-bit key and 128-bit block size to 128 blocks, we can actually think about a whole set of AES-like boxes, right? I say AES-like because they're not AES, they're just all the block ciphers that have this particular syntactic signature to them. So let's let us think about what that looks like. So let me introduce a bit more notation here. let's introduce notation. BC, my writing is just terrible right now, BC of Kn. We're going to define this to be effectively the set of all block ciphers with k-bit keys and n-bit blocks. And if we were to write this mathematically, this is really, well, it's really just this. This is the set of all mappings that have k-bit keys and n-bit strings and output n-bit strings, subject to the condition that each of these e sub k is a permutation. So this is the set of all block ciphers with k-bit keys and n-bit strings. If I were to draw this as a set, you could think about this as, let me draw a little circle here. So here's our set. This is the set of all block ciphers. Put this away. So this is, let's say, BC of 128, comma 128. How big is this set? In fact, let's do this. Would you pause this video for a second and see if you can answer the question, what is the cardinality? How big is this set? Pause this video and see if you can think about that. So normally when I ask this question in class, I get lots of answers. I get answers like, well, like 2 to the n factorial, or 2 to the n factorial, or things like this. People always seem to have kind of the idea that there's probably a factorial involved somehow, and there's also probably a 2 to the n that's involved somehow. And the intuition for this is reasonably clear. I've said that e sub k is a permutation for every k. So actually, let's maybe ask the simpler question. If we define another set, which we'll have use for as well, let me define this in a different color. Let's define another set, perm. So perm n is the set of all permutations. Set of all permutations. Over 0, 1 to the n. Set of all permutations over 0, 1 to the n. If I ask you how many are here, I ask you what's the size of perm n. I think most of you, after just a few seconds of thought, would say 2 to the n factorial. Why is that? Well, it's because we're taking mappings over n-bit strings. There are 2 to the n n-bit strings, and we're saying I want to know every way to permute a list of 2 to the n strings, and we know that's 2 to the n factorial. Yeah? So somehow the size of this set, the set of all block ciphers with 128-bit keys and 128-bit strings, is going to be related to the size of the set perm 128. Yeah? And the reason it's going to be related is because we've said that for every key, the block cipher is a permutation. In particular, it's a permutation over this set here, right? So, okay, having said that, how big do you think that this set is? Well, I'll just tell you, and then we'll sort it out. The size of this is 2 to the n factorial raised to the 2 to the k. Well, in particular, this is the general form for BCKN, with k equal n equals 128. So the size of the set of all block ciphers with 128-bit keys and 128-bit blocks is 2 to the 128 factorial, which, by the way, is already a number that's so astronomically large that it's It's way more than the number of atoms in the universe. I take that and then I raise it to the 2 to the 128. That's how many block ciphers there are. If I took every single possible bijective mapping that had 128-bit keys and 120-bit blocks, so every mapping of this form, however I choose to make these mappings, right? If I took every mapping that was a permutation with this signature, that's how many of them there are. Now, in particular, I can't even begin to possibly draw this to scale, but that dot there is AES. AES is one element out of this set, right? Because we've said that AES, remind you, we said AES is it's a block cipher, right? And it takes a 128-bit key and has a 128-bit block, which means that AES does indeed live in that set. It does live in this set, yeah? So here it is, although, of course, this point is nowhere even near to scale because this is exactly 1 point out of 2 to the 128 factorial raised to the 2 to the 128. So clearly not to scale, but it makes the point that AES is one particular element of the set of all block ciphers. And what makes AES AES is the way that this mapping is actually induced. And we'll talk about that in a later lecture. Okay, so AES is 1 point in there. Maybe it's worth making sure you see where this number came from. How did I get this number? Well, let's go back to thinking about permutations for a second. So I said that of permutations, that there are 2 to the n factorial permutations over n-bit strings, and we explained why that was the case. Whenever you think about any kind of a function, or whether it's a permutation or not, you can think about it as filling in elements of a table, right? I mean, every function, no matter what it is, you can think about it as a table where the, what am I doing here? That's not what I'm going to do. I just want the bloody pen. Give me the pen. There we go. As every function, right? Any function f I can think of as just like filling in rows. Got this table here. And the rows, so let's say this is some function, I don't know, f, little f. You can think of the f as being described by basically just a lookup table, right? And the rows, so let's say that f is a mapping from n-bit strings to n-bit strings. So we can think of the rows as being labeled. So here is 0 to the n. This is the string that consists of all n's. This is 0, 0 ending with a 1. This is 0, ending with a 1 and 0, and so on all the way down to the very last string, which is going to be the all ones string. So if f is a mapping that takes n-bit strings as inputs, and let's say it outputs n-bit strings as well, we can think about, if I wanted to count how about just all of the mappings? Let's do all the permutations first. All the permutations, we said that there are 2 to the n factorial, and an easy way to see that is by realizing that the number of ways to fill in this element here, there are 2 to the n ways to fill in this value. So 2 to the n choices for this part of the table. Now, how many choices are there to fill in this part of the table? Well, we know that there are 2 to the n minus 1 choices because, if it's going to be a permutation, then it can be any value except the one you just used. And there are 2 to the n minus 2 choices for this one, and so on. And by the end, there's only one choice left, right? So this is where you get 2 to the n factorial from, because there are 2 to the n, and for every one of those choices, there are 2 to the n minus 1 for this, and 2 to the n minus 2, and so on. So the number of ways to fill in this table is 2 to the n factorial. And indeed, that then counts all the ways to write down a function from n-bit strings to n-bit strings. So I didn't say this, but this is also n-bit strings. So the number of ways to write down all of the tables that map n-bit strings to n-bit strings in a way that is a permutation is 2 to the n factorial. I might ask you on the side to think about how many ways are there to fill in this table if I just want to know functions f. So maybe I'll just put that down as a side question. how many functions? From 0, 1, n to 0, 1, n. It's a separate question for you to answer. We've just said the number of permutations, the number of ways to fill in this table that are bijective is this many. I wanted you to figure out on the side how many ways there are to fill in if I just lift the restriction of being bijective. Okay, so fine. That gives us a way to think about how we get the number of permutations, or the size of the set perm n is by this. Now, how do I get from that to this? Well, every single one, if you think about a block cipher as a function family, each one of those being an e sub k, and you let me then just change this thing from an f to e sub k. So I changed the name of this thing. This is a table for filling in e sub k, right? Just change fix some particular k. In fact, let's just go ahead and be really concrete about it. Let's say that the particular k that we're thinking about here is the k that is the key of all zeros. So I want to fill in the table for E for the key that's the all zeros, the 128-bit all zero string, right? So n here is 128. So how many ways are there to do that? Well, I'm required to have this table be a permutation, right? So all these n's become 128s. So 128, 128, and so on. This is actually a 128. So we've just said, okay, the number of ways to fill in this particular table is this many, 2 to the 128 factorial, right? 2 to the 128 factorial. Okay, fine. Now, what about if I pick some different key down here? So what if instead of the all zeros key, what if I pick the all ones key? If I change this now to be the table that has the all ones key. Well, again, there are still 2 to the 128 ways to fill this in. Notice I didn't lose 2 to the 128 factorial, sorry. I didn't lose any of the possible ways to fill this in because I never said that there had to be any relationship between what e sub k, its mapping, and e sub k prime for any other key k prime. Those mappings are could be completely independent of each other, right? So in particular here, I'm trying to count all of the ways that I could fill in some family of e sub k's that are permutations. So there were 128 factorial choices when I had the all zeros key. There are 128 factorial choices when I have the all ones key. In fact, for every single key, there are this many ways to fill in the table that is the block cipher under that key. So that means I have 2 to the 128 factorial for each key, and there are 2 to the 128 keys. So that's where this number comes from. You can think about a block cipher if you like. It's really kind of goes along with this function family idea. It's kind of being like a filing cabinet, right? So you've got a table for e sub k of 0, and then you've got another table behind it for the next key, another table behind it for the next key, and so on. And that there are 2 to the k of these tables, and each one of these tables, there are 2 to the n factorial ways to fill them in, and the choices across tables are independent. Okay, so that's how we get the sizes of perm n and of BCKN, the set of all block ciphers with k-bit keys and n-bit blocks. And we've said that AS is one particular tiny point inside of this massive, truly massive set.